All right. In today's class, inshallah, we'll be talking about the measurement of volatile organic compounds. Do you guys remember the volatile organic compounds? VOCs from VOCs, do you know? VOCs. VOCs are the compounds that partition between the liquid and the gas. So similar to the gasoline that you have in the station, that's why you smell it. Similar to the marker that you put, similar to the paint that we do on the wall, that has a part that in the liquid and part of it evaporates. And if you keep it like in not in a closed volume, but you keep it an open volume, it will keep evaporating and it will keep evaporating. All right. So VOCs are one of the most important pollutants. And remember, they are the only ones who are not a direct pollutant. They are not in the NACs. But why are they so important? Because they are the precursor of ozone. And ozone is really one of the most important problems of current days. For VOCs, they contribute to the ozone directly. So now in this class, I divided into two parts. The first part is the measurements of the VOCs, and the second part is the control of VOCs, because I thought they are really two big parts each of them. So the importance of controlling VOCs, I have a mistake typo here. The health risks, some VOCs, for example, benzene, are toxic, posing risks like respiratory problems, headaches, and even cancer. Environmental impacts, the VOCs are significant contributors to the photochemical smog. VOCs react with NOx in sunlight, forming smog, and you have the ozone formation, the ground level ozone, a harmful pollutant, and climate impact. Also, some VOCs, similar to carbon dioxide and methane, absorb infrared radiation, contribute to global warming. So governments worldwide set strict VOCs limits to reduce air pollution and protect public health. The industrial impact is the control measures reduce emissions from industries, transportation, and everyday products. As you can see, that VOCs come from some industries, for example, printing press, all the books, the newspapers, anything that's being printed, even regular printers, posters, they include VOC. Why? Because everything is dissolved in a solvent and it evaporates. While it's evaporating, this is a pollutant that's being emitted. Any painting activity, cars, houses, whatever, that's also emits VOCs. Any the greasing, which is a very important step in a lot of industries. Basically, when you are working with tools, you always have to clean them. And while you're working, because they got like blackish color, right? If you think about it in a workshop or a mechanic or something, you'll find all their tools are black. So what do? They put in a solution, right? That takes away this dirt. This solution is a solvent. Similar to the acetone that the girls use for removing nail polish. So because these solvents, they are all volatile and they contribute as a VOC. So all of these are emitters of VOCs, but that's not it. Oil and gas, and that's a very big contributor here in UAE. So that's a very big emitter of VOCs. There are direct VOCs which are emitted just by exploration. When you are looking for methane, natural gas, when you are looking for oil, always there is gas that's with it, and this gas are VOC. Remember, the VOC is finally it's hydrocarbon. If you go back to the class of the organics, so it's all hydrocarbons, similar to methane. You can always burn them and get them and use them as a fuel. So they are part of the oil and gas layers. So when you are exploring and opening new concessions for oil and gas, you are actually releasing a lot of VOCs. And this is new. That was not been really known before. They started the first regulation about VOCs from oil and gas exploration was 2015. See that this is always evolving field. VOCs not only from exploration, but also from any combustion. So anything that combusts, engine that combusts, it also produces some VOCs. Why? Because of incomplete combustion. Remember always that the gasoline is also an hydrocarbon. And when you are burning it, itself is, some of it is being transformed into VOCs while it's being completely combusted into CO2. So you always get VOCs coming out of combustion as well. There are also other natural processes that emit VOCs, such as fermentation. You know, when they do the yogurt, or when they do the pickles, or when they do the alcohols, all of this, you are using bacteria that does a specific metabolic function, and within this metabolic function, VOCs are being formed. So you come up with a lot of VOCs such as acetaldehyde, formaldehyde, methanol, and so on. Any questions so far? All good. All right. So now that we've talked about the importance of VOCs and controlling VOCs and measuring VOCs, let's look at this graph. This graph shows the relationship between the x-axis, we have temperature, and the y-axis, we have the vapor pressure. 4 different VOCs. Every line of this is different VOC here. And we can use this graph to estimate the vapor pressure at this temperature. So what is vapor pressure? Anybody? No? What is vapor pressure? Okay. So the definition of vapor pressure is the pressure after which or above which there is no more phase transfer from liquid to gas. Again, it's the pressure above which there is no more transfer from liquid to gas. We covered this early in the class. Remember saturation, subsaturation, supersaturation. This is the vapor pressure. When you have in this cup, when you have a solvent, and then you have this cup open, the solvent will keep evaporating. If you leave it a few days, you will not find the solvent anymore. That's true, right? You can put, you have always seen that. You can put stuff in a cup and then you come a few days later and you don't find it. If you close this and you make sure it's completely closed very well, some of it will evaporate, but after a few days, you will come and see the rest of it. It will smell when you open it. It will smell like there is stuff in the gas. However, the liquid will not be decreased very much. Why is that? This is because some of this gas liquid that's evaporated filled the gas and kept building up pressure in the headspace until we reach the vapor pressure. Once we reach the vapor pressure, no more liquid can evaporate. So this is the boundary of evaporation. When we open it, we equalize pressure. Now it can evaporate again. As long as it's closed, we are building up pressure. Does it make sense? And where do we get the vapor pressure? From this figure over here. So the first law that is very important when we are talking about VOCs is Raoult's law for VOCs mixtures. Raoult's law helps us predict the concentration of VOCs in the air when in equilibrium with their liquid form. Yi is equal to Xi times Pi over P, where yi is equal to the mole fraction of component I in the vapor phase, xi is the mole fraction of component I in the liquid phase, pi is the vapor pressure of pure component I, P is the total pressure of the system. So the mole fraction of I in the vapor is equal to the liquid times the vapor pressure over the total pressure. And you can really understand that yi over xi, which is the vapor over liquid, is equal to the vapor pressure of the pure compound over the total pressure. So here is an example. Calculate the water vapor content in air in equilibrium with pure water at 68 Fahrenheit, which is 20 Celsius. So here we'll assume that xi is 1, and always because it's water, right? That's the concentration of water. It's 100% water in liquid phase. Small amount of air dissolved in water is negligible. Now let's go back to the figure and look at water at 20 degrees Celsius, which is 68 Fahrenheit. So let me get my pointer. So where is 68 Fahrenheit? Is about here. And we'll go up to look for water. Do you see it? I really don't. Where is it? This one. So, because it's here covered with the meeting. Okay, that's water. It's very hard really to read, but at 68, I think it's this one. It's about 0.4 or 0.5 psi. So let's see what was 2.3 it was. Yeah, it was 0.023. That's an atmosphere. So, but you can convert from PSI to atmosphere, or you can use the Raoult's law directly with PSI. So the most important thing is this ratio, PI over P, has the same units. So you can have the P in PSI or atmosphere, and then you will have to get that in atmosphere. So then it is 1, which is, our assumption is 1 times 0.023 atmosphere over 1 atmosphere, which is equal to 0.023. And that's the mole fraction of water vapor in air, or 2.3%. Next example is about the calculation of the vapor phase composition of 50-50 mole percent benzene toluene mixture in equilibrium with air at 68 Fahrenheit in a closed container. Given data, mole fraction of benzene in liquid is equal to 0.5. Mole fraction of toluene in liquid is 0.5, so they are 50-50. Vapor pressure of benzene is 1.45, that's from the figure. Vapor pressure of toluene is 0.42. Total pressure is 14.7. So we will do Raoult's law once for benzene and once for toluene. Then that's 0.049. Similarly for toluene. So in order to get now the Y for the air, that's 1, which is the total, minus the fractions of the benzene and the toluene. So 1 minus 0.049 minus 0.014, which is equal to 0.937. Any questions? Next equation, important, is Antoine's equation. Log P is equal to A minus B over T minus C, where P is the vapor pressure, T is temperature, A, B, C are constants. And you can either given this or you can get it from tables, the A and B and C. So estimate mercury's vapor pressure at 20 degrees Celsius by extrapolating data using the Clausius-Clapeyron equation, which is the same equation. Vapor pressure at 329, this is given data, Fahrenheit equals 2.1 psi. Vapor pressure at 700 Fahrenheit equals to 18.93 psi. Temperatures converted to Rankine. So Rankine is the Kelvin in the British system. So 329 plus 460 equals to 789, and 700 plus 460 equals to 1160. Now we use this equation. We'll say that we'll do it twice. Once for the first condition, once for the second condition. So log 0.1 is equal to, yes. Yeah, either in this case, we are looking for the constants. But you can, sometimes, most of the time, actually, the normal that will be given for direct application. So log 0.1 equals to A minus B over 789, and log 18.93 is equal to A minus B over 1160. So solving for constants A and B, we'll get that A is equal to 6.11993, and B is equal to 5617 Rankine. So we'll use the equation. Log P is equal to A minus B over T minus C, which now we know the A, we know the B. T minus C, in this case at 20 Celsius, is 528, which will be equal to minus 4.519. And here are just the value of P in different units. In that T is required in the example at 20 Celsius. So it gives us two values, 329 and 700. But the question is asking about 20. So basically we use this two to get the constants, and then we reapply the constants to get it at 20. Now, C here is not really, you assume that it's equal to 0. So P is equal to 3.02 times 10 to the power negative 5 psi out of this equation, if you get the value of P, and if you convert it into atmosphere or torr, so you'll get it with these values.
What's negative 4.5?
Negative 4.5. That's the log P. Log P, that's just the solution of this equation. 6.11 minus 5,617 over 528.
How do you get this P?
When you have log P is equal to this number, how do you get P? You get 10 to the power, and the calculator, you can do inverse log, which is 10 to the power on both sides. So 10 to the power log, then it's P, and then 10 to the power the other negative 4.5, that will give you the 3.02. You have your calculator with you?
We estimated
it's given at 20, so 20 is equivalent to 528 Rankine. And usually I will not really go to Rankine. It's just the example. So here you go. Log P equal to negative 4.5. So you want to inverse log 4.5, negative 4.5. See, not inverse, shift log negative 4.5. That is equal to 3.02 times 10 to the power
okay.
negative 5. Because log P is equal to this number. So inverse log to get the P, which inverse log is 10 to the power negative.
We can leave it as yes.
As PSI. This is just conversions for you. All right, I'll just let me for a second stop the video here.